So I just want to emphasize the importance of free body diagrams. So when I look at this, I see an arrangement of discs that are all hanging. The tensions in each of those smaller sections of cord are given. The tension, the top loop over the frictionless pulley gives a pull force of 98 newtons, and that's attached to the wall. So the question is to figure out the masses of each disc. And I want to quickly show you how similar the free body diagrams are. So I would start this problem by looking at mass A first. Right, here's mass A. And from mass A, we've got a tension force from the pulley. I'm going to call that FTP. On mass A, what else do we have? We've got pulling down on mass A, two things. We've got the tension in rope 1, and we've got the weight of object A. Now, although you might want to ask yourself or think, well, what about the weight of mass B and mass C and mass D? Aren't they all pulling down on mass A also? The answer is yes, they are. But where are all of those weights being taken into account? The tension. Look at FT1. FT1 is how much this rope is pulling down on mass A. So FT1 already is taking into account all of the things below it. So this tension that's felt here is a result of these three masses all pulling down. That's what creates this tension right here. So FT1 is really taking into account all of these masses. I'm doing this right now on purpose because a couple of you are still trying to draw masses affecting each other that are connected by ropes. If they're ever connected by a rope, they don't affect each other directly. They affect the tension in the rope, and then that tension then affects the other object. So again, this is just mass number 1. Okay, this is simply mass number 1. Now let's take a look at mass number 2 and how its free body diagram differs. I'm saying A, sorry, 1 is A and then B. I'll make it look better. There's A and B. So for the second mass, this is mass B now, we've got that tension pulling up from rope 1 still. Well, last time it pulled down. And take a look at it. That makes sense because that rope connects mass A and B. So this rope right here I'm pointing to, it pulls down on mass A, and that's shown in the first diagram. But in the second mass, we can see that this mass is getting pulled up by this tension now, and that's showing it upward. So just like I mentioned in class with tension forces, they're always going to do what? They're always going to do one thing. They can only do one thing. They can only pull. They can't push. Tension cannot push. So then from the bottom of the second mass, or mass B, we've got the tension in the second row pulling down. But then we've also got the mass, or the weight rather, of object B. So look at object A and B. Their free body diagrams are the same. They both have a rope pulling up, they both have a rope pulling down, and they both have their own weights pulling down. So mass A and mass B, although the numbers will differ, and I understand that, free body diagram-wise are the same. Tension up, tension down, and then they both have the weight acting down.
Is FGB a sum of masses for FGB?
So FGB is the weight of object B. FGA is the weight of object A. So this weight right here is the weight simply of object B. Remember, so when we draw a free body diagram, only that object's weight can act on itself. If those objects were physically stacked on each other, which we're going to see in a little while, then we're going to have two different weights pushing down on one location.
Okay.
So the tension FT2, see how this is pulling down? That FT2 is the tension in this rope right here, which is already taken into account these two weights. So we don't draw these two weights acting on object B because the tension in the rope is what's pulling object B. Okay. And we're going to see that now in the next one. So if we look at the free body diagram of object C, we see the same thing here. We see the tension in rope 2, right? Tension in rope 2 pulling up on object C. The tension in rope 3 pulling down on object C. And then we've got the weight of object C. So A, B, and C are the same. All three of them have the same free body diagram because they all have their own weight, a rope pulling up, and a rope pulling down. What differs is all of my subscripts. 1, 2, 3, A, B, C, P, 1, 2, right? That's what's different. But the concept for all of them is the same, except for mass D. Except for mass D. how does mass D, its free body diagram, Matt, differ?
There's no tension going down, right?
Good. We've only got the tension in rope 3 pulling up. We've got the weight of object D pulling down. And that's it. That's all we've got for mass D. Now, I'm not going to spend a lot of time going through the solution because the solution is just algebra at this point. Look at all the givens in the problem. Watch what I'm going to do just so we can mentally see it. I'm going to put a check next to all the things that are given. Okay, so FT3 is given. FT2 and 3 are given. FT1 and FT2 are given. The tension in the pulley and FT1 is given. Everything with a check is given in the problem somewhere. So how many unknowns do I have in this problem? Looks like 1, 2, 3, 4 unknowns, right? The weight of each mass. Well, how many equations are we going to have? One equation here, equilibrium. Another equation here, equilibrium. Another one here, equilibrium. Another one here, equilibrium. So we're going to have 4 equations and 4 unknowns. So we could just solve these all independently. This is given. Well, FT1, we don't know it until we get it from here. We won't know FT1 until we know FT2, which we get from here. We won't know FT2 until we get FT3, which we get from here. So where should I start this problem? Over here, all the way on mass D. Because on mass D, I can get this value here. I can get all of these unknowns. So actually, I'm sorry, we're given all the tensions. I'm saying as if we don't know them. We could start with any of these in this problem. Some problems, though, I was thinking of a different one I was looking at. Some you will not know the tension in the other chords until you get the previous one. So say in this problem we were given this weight and we had to figure out this tension. We'd plug that tension in to get this one. Plug that one here to get this one. Plug that one in here to get this one. But in this problem, it's a level 1. I forgot. It's easy to give you all the tensions already. So it doesn't matter where you start actually here. You could find any of these automatically because they're all givens. So I'll demonstrate for mass A. So for mass A, I'll demonstrate for this time. We have FTP acting up. That's the tension from the pulley. We've got FT1 acting down, the tension from the rope. We've got the weight of object A acting down. And we know that this is in a state of vertical equilibrium. And that's the mass of object A, if we were to calculate it. Yeah, but it's in a state of vertical equilibrium because it says, or we're told here, that it's an arrangement, it's suspended over chords, there's nothing about motion whatsoever. It's not raising it up or lowering it down with any acceleration. It could be, right? The chord could be retracting or extending and therefore lowering or raising, and then you would have acceleration. That would make me think of what problem? With an object that's vertical and something's accelerating vertically, what problem is that? What's the standard problem, the classic problem we talked about? Yeah, what is it?
Elevator.
Like the elevator problem. Yeah, good. I call it the elevator, but yeah, anything accelerating vertically, right? The elevator problem. It's a nice way to think about that problem. Because if this object was suddenly moving up and down, it would be that. So this would allow you to solve for the mass or the weight. In this case, they want mass, I think, right? Yeah. So you'd have to divide and solve for m. But in this problem now, what we can do is we could solve for this right here, which is what we're looking for, in order to get the mass of object A. If we get the weight of object A, we can just divide by 9.8 and get the mass of object A. And then we would do the same thing. The next 3 equations would all come from the other 3 free body diagrams. That would allow us to solve for all 4 weights and therefore all 4 masses. All right, second problem for today. So here I want to point out again that free body diagrams are really important. And what else is really important in this problem? The subscripts, right? Look at the subscripts. Those matter a lot. So if we're not using proper subscripts, we're going to run into problems along the way. Let's take a look at the second example. So now we're going to jump right into the elevator type problem here. A lamp, we didn't do this one, right? This was not homework? Yeah.
So when you have 2 blocks that are pushing on each other, and you're asked to find the force one block pushes on the other, how would that...
It's like tension. That would be the same concept of tension. With tension as ropes pulling between, this would just have the interaction of the 2 forces pushing each other. So if you recall, we did one of them in class, Kara. Do you not? Yeah, you might want to look it up, but if you recall, it would look, and this is not for this problem, by the way, this is not for number 44. So if you were applying a force like this, F applied here, right, on mass 1, and this is mass 2. If I draw the free body diagram of mass 1, I've got the applied force, F, acting. I've got its weight acting down of mass 1. I've got the normal force, and then I've got the applied force on mass 1 from mass 2 pushing back.
Right.
Then mass 2, I would have the applied force on mass 2 from mass 1. I'd have the weight of mass 2, and then I'd have the normal force acting on mass 2. So see F12 and F21? They're equal and opposite each other. It's the same value and magnitude, just opposite in direction. Okay? That's how the generic look would be. And if you recall, Kara, the nice thing to do with this would also be to draw a lumped equation, remember? Of m1 plus m2, the acceleration of the whole system. So you're going to have 3 equations of motion here in the x direction. You'll get one equation of motion from this one. You'll get a second equation of motion from that part. And then you would also say at the very end that the overall force acting on the whole system is F. And you could say that equals m1 plus m2 times the acceleration of the system. That would be looking at the entire system as one giant free body with only this force acting on it. See what I'm doing here? I'm drawing like both masses as one giant mass and looking and thinking, well, the overall force is acting on that one giant mass. That's the overall force. That's the sum of those masses times A. And then we'd have an equation of motion here, and we have an equation of motion here. Okay, so we have 3 equations of motion. You have to be given information to solve.
Okay. The blue is the free body diagram, or just the system.
The blue is the system. So those go together. And then the equation here would be F minus F12 equals M1 times A. The equation from this guy over here would be F21 equals the mass of the second object times A. That's what our system would be. You have one equation here, one equation here, one equation there. This is a two-body system question, two-body system. So let's look at 44 though. Let's take a look at 44. Okay. So we've got a lamp, it hangs vertically. We're looking at an elevator that's descending. It's descending, descending. It's decelerating also as it descends. What does that mean to you? It's descending, but it's decelerating as it's descending. Give me a description of how you would talk about this. Yeah.
It's like slowing down as it goes down.
Good. Slowing down as it goes down. Very good. Therefore, which way is the acceleration acting on this body? Max? Upward. The only way it can slow down is if its motion is down and acceleration is up. Remember that concept, right? The only way you decelerate is if acceleration opposes your motion. So in the first part here, in part A at least, we know that the acceleration is going to be acting vertically upward. So the acceleration equals 2.4 meters per second squared. And it's definitely positive because it's acting upward. We know that if we think about a lamp hanging from a cord in an elevator, we're looking at here's the lamp, there's the cord pulling up with tension, here's the weight of the lamp acting down. For a full diagram, here's what it looks like, right? Okay, that's our problem here. Motion is downward, as Bridge told us, accelerating is upward, and we know that this is the object hanging in the elevator. But that's the free body diagram. It's quite simple this time, right? Ft and Fg. So we know from this first portion here that Ft minus Fg is going to equal Ma. A is given in the problem. A is given as 2.4. In part A, we're given the tension, and we're to find the mass of the lamp. So let's solve this algebraically. The weight of an object is mass times gravity, so we replace mg in for Fg. We could then move it over to get m on the same side. We could then factor out m to get m by itself. And finally, last but not least, we can then divide by the quantity g plus a. And that's going to be our mass in this problem. So I want you to start doing it this way, and I keep pushing you to do it this way. So the more you practice, the easier it becomes solving all with variables here. So what do we notice here? What do we notice? The mass of the object here would be a function of these 3 parameters here. So the more tension in the rope, it means the object has to be more massive. That makes sense. Think about it logically. Hang on to a rope if you're heavier. If Chip hangs on the rope, who's taller, Chip probably like 175, you're pretty tall guy, right? Around there? Honestly, something like that? Okay. Versus Bridge, You're probably by weight 150, 140, somewhere in there, 160. Okay. So if Chip hangs on this rope, there's going to be more tension because there's physically more mass on the rope. It's just a matter of like common sense there. And take a look. The higher the tension in the rope means it came from a higher mass. They're directly related to each other. It's logical. Now, this part is not as nice to understand and see. It'd be easier to see it if we were to solve for tension by moving that over to see the connection. How does part B differ, though? That's part A. How does part B differ? How does part B differ? Yeah, Matt, what do you think?
Well, I was thinking like if you could just use that same equation, would it be G minus A instead of G plus A? And
Why would you say G minus A?
because it's going upward. Yeah, because it's accelerating upward, so the
So it's moving upward, right?
yeah.
It says ascending, so moving upward. And it's upward acceleration also. So it's not the exact opposite of the last problem, right?
No, because it would be gravity was stronger because there's more acceleration.
Think
down.
free body diagram now. Think free body diagram and think motion picture really. Has this changed at all?
No.
No. Everybody agree this is not going to change here? Now, motion though is now up instead of down, isn't it? But the acceleration is still it's still up. It still has an upward acceleration, doesn't it? So, what's the actual answer, Chip?
It's the exact same.
It's the exact same thing. It's very tempting to want to switch part B.
But what the tension?
It'll still be 89. Yeah, we'll get that same answer. We'll use 89 because we still.
Tension come from a different place though. Like if it's like accelerating upwards.
Oh yeah.
Land
It's
is
still the same.
Land
The land is still pulling down on it
Yeah.
because it's accelerating upwards.
F equals ma.
It's the same exact equation, is what I'm saying. This doesn't change. It's very tempting to swap the sign of acceleration because you think, oh, now it's accelerating, whereas last time it was decelerating, right? Do you see what I'm saying? So it's very tempting to change acceleration. But you have to think in this section, remember, free body diagram. Up is positive, and it's still accelerating upward. Okay? It was kind of a trick question. Sorry to set you up there, Matt. I thought you had it because the way I saw that spark or that look, you're like, and I'm like, oh. But you got the concept of like sometimes you're going to switch acceleration, right?
Yeah.
And that would be if it were going upward now and it were decelerating still. Then acceleration would be acting downward, and then this value would be negative A, or it would be negative 2.4 instead of positive.
So
Okay?
motion doesn't really matter as long as it's more the acceleration.
Hear that? That's the conclusion from this problem right here. Nothing in this problem asks us about velocity. Velocity is not used in this problem. That's all that changed here. Velocity went from being negative to velocity being positive. But acceleration in this case, in both scenarios, was still acting upward, which in our problem we call upward positive. I keep insinuating or keep implying how important it is to recognize what you call up and what you call down, right? Because we call up positive, which we're always going to do, please always call it positive. It'll just make life easier for all of us, so we're all on the same page. If you always do that, and you have an object accelerating upward, whether the motion is down or the motion is up, that does not matter. Okay? So it's the acceleration that matters most. This would be 89 over 9.8 plus 2.4. And the next part of the problem, by the way, says find the tension. It doesn't say find the mass. So it says, what is the chord's tension when the elevator ascends upward? So you would just solve this equation for tension right here, and it would be Ft equals m times g plus a, which is really this equation right there. And we'll get the same answer because we're going to use the mass we got as an answer for part A. We're going to plug that mass from part A right there. And this is still going to be 9.8, and that's still going to be 2.4. So we'll still end up getting the same answer for Ft, which will be 89 newtons for the second part. I don't know what the first part comes out to be for the mass here, whatever this turns out to be as the answer. 7.2? And that's the mass, so that number would go right here. Okay. So a very interesting problem to think about because you want to switch the sign. You want to say, oh, something's going to change, but it turns out nothing changes. Nothing changes. Okay. You want to keep going? Oh, yeah, go ahead. Go.
Okay.
Doesn't matter.
So when there's no horizontal motion, upward is positive. But when there's inclines, downward is positive.
No. So be careful what you're saying right now. You're saying up and down. So up is always positive, down is always negative. When it's an incline, you say down the ramp
Down the ramp.
and up the ramp.
Okay.
Not the same as up and down. Because remember, up and down is our y-axis, and we're tilting that to be perpendicular to the ramp. So if this is the ramp, now this is up and this is down on a ramp.
Right.
This is down the ramp, this is up the ramp. I don't know, that sounds ridiculous, but they are different in what he's saying.
Okay.
If you want to call this the parallel force and the perpendicular, some books do that for ramps. You're welcome to do that, that helps it, those two. But if there's a mass attached to that carrot, like over a pulley, which we've seen a lot of, then the one that's hanging there, up is still up and down is still down the way it normally is. So if you attach this inclined plane to another mass and that mass is hanging, this is up, this is down. This is up out of the ramp, down out of the ramp. This is down the ramp, up the ramp.
So why is it positive in this case for upward?
Because it's just an elevator.
Okay.
And this is not a ramp problem.
So, okay.
Up is positive, down is negative. That's going to be the same. So let me show you what I mean for the diagram-wise. Before Kara started asking about this one.
Yeah, I figured it. I was wondering. Yeah.
Give me 1 sec, and I know Matt was waiting too. So let's look at like an object like this. Like one of these scenarios. So this is considered up. This is considered down. This is considered the positive x, or down the ramp. This is considered the negative x, or up the ramp. Then finally over here, this is considered up, this is considered down. That's how I would orient my orientation every time. Okay, if I reverse the diagram, well, down the ramp, which was coming what looks like downward and left, will now be downward and right, and that will still be considered positive x, or something like that. Okay? Again, my recommendation, you can choose your own methodology, but be careful about your signs. I'm trying to teach you guys a certain way that allows the signs not to get mixed up. Why is that? Can you all take a look? This is like probably, I'm glad you asked this. What I'm about to say is probably one of the most important things in this chapter. If this object accelerates, or objects, the system, which way can it move? The system as a whole either can move, what would we call this direction? No, what am I moving? So how would I call this? Counterclockwise or clockwise, right? So if I look at this, look carefully please. If I look at both masses, this mass here and this mass right here, if they were to move together, the system would move like this, right? Take a look at where I'm pointing. This would go up and this would go down. Aren't those both considered positive directions? Do we see that? That would make both of our accelerations positive. If they both went down like this, take a look please. If the system went like this would be going in the negative acceleration. This would be in negative acceleration also. So if you remember the last quiz I gave you, quiz 7, that affected the problem a lot. Some of you didn't have to make one of them A and the other negative A. Others of you had to do that based on your diagram. If you trust me on this, and you make your diagram the way I'm showing you, then you won't have a problem. Because the only way the system will work is if when this one goes down the ramp, this gets lifted up. So I want to call those both positives. So that my acceleration is both positive, or so my acceleration are both negative. I don't want to have opposing positive and negative because it just gets confusing. If I have to do that, I'll do it in certain scenarios, but I don't want to do that is what I'm saying.
And then an elevator problem would just be half that. Anyway.
Yeah, the elevator is just everything on the right side only. Yeah? Maroni, you had a question? Okay. Chip?
Like, so when you're trying to figure out like what the acceleration is, could you look at like the concavity of the direction of motion? So if it's like concave up, it would be a positive acceleration. Because right, it would either be decreasing at a decreasing rate coming to the stationary point, or increasing at an increasing rate.
You can. Concavity, second derivative acceleration. Well, you're not talking about the curvature of tension on the road.
No, I was just asking you before to like figure out what the direction of the acceleration is, right? So, and if it was concave down, you'd be increasing at a decreasing rate, or
Would be increasing at a negative rate.
yes.
Yeah, you can think of it that way.
Going
Sure.
on with this other.
I like the idea. It's right. Concavity being the second derivative, being acceleration. Yeah. Calculus thinking, right? Yeah. So this is really interesting, by the way. I did not think this was funny, but the book says some of the funniest videos on the web involve motorists sliding uncontrollably on icy roads.
That was funny. That's
So I thought of, right? You know what I thought of is, I thought like, well actually like kit mittens. Ever seen kit mittens?
I like that.
Anyone hear kit mittens before?
Can we put this in his bridge?
Bridge with like mittens on his hands and feet, running and sliding across the floor. But literally, this is a good problem, right? The idea is we have some friction, we have less friction due to ice, that's part B, and then we have ice on an incline or a decline. So what I would actually think about, and these actually are kind of funny, these ones are really funny. An empty school bus, empty, mind you, on a road that's icy, that's slightly inclined. Have you ever seen these videos?
Yeah, but it's like,
The bus just won't stop. It just will not, and it starts crashing into cars. Oh yeah, there's a couple of these where like it's a really icy day, the bus driver will park it, and as the day goes on, it gets icier, and the bus will just pick up some momentum somehow, and it won't stop going downhill. It just keeps picking up momentum until it crashes into enough cars to get like pinned, and it's going down like this, and it gets pinned like perpendicular to the road. There are a couple videos on these actually. That's kind of fun, and that's the third part I'm thinking about here. But when we get there, and it's an empty school bus, so I'm not encouraging death. I promise. So anyway, the question is this. We want to take a look at stopping distances, which you kind of did with that lab. Give me a break if you remember back, last quarter. Remember how slide give me a break, for instance? So we're looking at a problem where we have an initial speed of 10 meters per second on a dry road, an icy road, and then an icy hill. So let's take a look at part A. How far does the car take to stop on a horizontal road if the coefficient of kinetic friction is given? We assume that when you hit the brakes lock and you start sliding. And if you know anything about cars, they don't lock. They have what's called anti-lock brake systems, where they start to oscillate, and the brake pad does not engage the wheel the whole time. It does this, so that it causes the brakes to engage, disengage, engage, disengage, so your wheels don't lock up and then you don't slide. And that's because static friction is greater than kinetic friction. So causing the wheels to allow them to slide and then stop, and allow them to slide and then stop, actually helps you with friction. Anyway, that's how anti-lock brake systems work. Here, though, the brakes lock up, the car slides down the road. We've got our mu value, typical for tires on dry pavement. You do not have to memorize this. All right, so let's take a look at this first example. So here's the car itself. It's sliding to the right. So we know that friction is acting to the left. I'm subscripting with a K, standing for what there? Kinetic. We know that normal force is pulling this up. We know that the weight of the object is pulling it down. And that's it. Remember, I don't draw the velocity. I know the velocity was 10 meters per second to start. That's fine. I'll write that down on the side. We know that the final velocity is going to be what for it to stop? Something that people sometimes disregard. They forget, oh, it's stopping. There's another given. We're trying to find the acceleration, really, I think, right? Let's see. Because we need the stopping distance, I think. So we really need both of those things. Think about it, right? If we want the stopping distance, which is what we're trying to figure out, that's delta x. And if I look at the equation that'll work here, the equation that'll work will be giving me a. This problem has nothing to do with time. You're going to notice that a lot of your force problems, time is not involved at all. So if you're going to use a kinematic equation somewhere along the way with forces, which is what we're about to do here, the kinematic equation is most likely going to be v squared equals v naught squared plus 2a delta x. Okay, just to give you a little idea here. That's going to most likely be the equation that you use with kinematics if it asks for like a stopping distance for a friction problem, which is a classic friction problem. Find the stopping distance involved. And on the exam, you can do this either with the work kinetic energy theorem or with forces and kinematics. Either way works. You can choose what you want on the AP exam. Because we're doing forces, I'm clearly doing forces here. So we've got the following. In the x direction, we've got negative friction equals max. And that's it. That's all I've got in the x direction right here. That's all I've got in the x direction. I know that acceleration, which is what we're going to solve for, is definitely going to be negative because we're slowing down. We know that for a fact. It's got to be negative here. We can solve for this, but if I go to try and solve, do I know FFK? Anybody? FFK? What is the value? What is the equation for FFK? I plug in. What do I plug in for friction always? Good.
Oh, 0.6.
Give me the general equation.
Yeah, mu times F1.
Very good. So recognizing already that it seems like, okay, we're getting there. We got mu, that's given, right? Mu is given in the problem. But Fn is not given, right? Fn is not given. So we're going to need to plug in for Fn. Well, let's at least solve for A first. Let's divide by m. So at least we have A. A is negative mu Fn over the mass of the object. That's the acceleration. We're going to take that value, whatever this turns out to be as a number, we can plug that number in here and then get x, right? Because we have this, we have this. We've got these two. We can get A, we can get x. So we have A, but we need Fn. See what I'm doing? I'm doing this on purpose. I'm leaving the variables, I'm not plugging in yet, so you can see what's really missing. So to get delta x, we need A. To get A, we need Fn. So we need inherently Fn. Where do we get Fn for any problem? Not any problem, I shouldn't say that, sorry. For most problems, where does Fn come from?
It's mg.
A lot of the time it's mg, but where does it come from is my question. What direction does it usually come from, I should say? What direction? Traditionally, yeah, the y direction, the vertical. Okay, and if we look at a free body diagram of the vertical, we've got it. It's at the top right there. So we know that Fn opposes Fg. So as Max said, for this problem, Fn is equal to Fg because of that equation right there. Right? This tells us that Fn is really Fg, which is really saying that Fn is mg. So this equation right here goes in for Fn. So what happens? Yeah. So how might we word that statement? We could say that the acceleration is, what's the phrase? That phrase on a test, right? We have to give verbal response at times.
No longer a function of
Good. The acceleration is not a function of mass. What's another way to say it? The acceleration is independent of the mass, as opposed to saying the acceleration depends on the mass. Right? Again, the acceleration right now, what does it depend on, actually? The acceleration depends only on coefficient of friction and gravitational constant. Everything else tends to cancel out in this problem. Okay, nothing else matters for this portion of the problem. Now, that is what gives me the acceleration. Let me zoom out a little bit so we can see a little bit more of this problem. Let's slide this over, actually. Okay. So that's what gives me the acceleration, right? Negative mu k times g. There's the acceleration. Now, if I solve this equation over here for delta x, recognizing that the final velocity is going to go to 0. Oh, nobody corrected me. Anybody see a mistake somewhere? Thanks, go ahead.
Yeah, I was going to mention it, but it's the VF squared.
Yeah, these two should be switched right here, guys. Please, feel free to correct me. Sorry about that. Okay? I had these mixed up. I put Vx and V0x in the wrong spots there. Now, again, the final velocity is going to be 0, so I'm going to drop that off. Take a look at what I just crossed off here. Okay, that's what I crossed off. So now I can solve this for delta x. Delta x is going to equal negative V0x squared all over 2 times a, where a, if we recall from the last line just now, was the following. So again, I'm taking this right here, which is equal to a, and I'm plugging it into that equation right there. So we did what looks like a lot of kinematic work, and I'll put a little divider here so you can see where I'm pointing to. All right, there's all the kinematic work in the top right corner. And to do the kinematic work, to find out the stopping distance, we needed acceleration, but acceleration came from our work with forces, right? And we looked.
That's part B.
We looked at the x direction for forces here. Then we looked at the y direction for forces here. We took our x direction for forces, got to the point where we got acceleration, but it was a function of Fn. So we needed the y direction to get Fn and plug it in here, which gave us the acceleration here, which we then plugged into the kinematic equation to get the stopping distance. So look at my answer. My final answer for stopping distance, I'm going to circle in yellow here. That's my final answer. And clearly, if I change my road composition, the surface, all that's going to change in this equation is what? In the yellow equation, what's the only thing that changes? If I change for part B, the composition, right? So I'm changing. If the road now has ice, all I'm changing is what?
Mu K.
Just mu K. This is still 10. The problem began with the starting velocity is 10. So no matter what scenario we're at, if it's dry ice or tilted, this is 10. Gravity is 9.8. Mu is what's changing from part A to B. So the answer for part A we're going to get for this is simply if we plug in at this point everything we know. So this is going to equal negative 10 squared over 2 times negative, what was mu? 0.6?
Yeah.
0.6 times 9.81. Or just say 9.8 for now. That's going to give our answer for part A. And then for part B, we're going to do the exact same thing. For part B, we're just going to change our mu value. Okay, so again, there's part A and part B. They're really no different at all. C is definitely different. So let's take a look at A and B and any questions first. Matt, go ahead.
Wouldn't that equation, like negative VIX squared over 2, whatever, wouldn't that be like something you could use in any equation where you're given that much data?
If you're given a scenario that can be modeled the same way, absolutely. But what if suddenly, like for example, it's on an incline, it's going to change for part C. Or if suddenly there's a tow rope pulling on something that's on an icy road. Now you've got tension pulling to the right, so the X equation changes. Do you follow what I'm saying?
Yeah.
So you're right, Matt, to notice that you could use this. So if I do this, and we talk about mitten kittens and Bridge wearing mitten kittens over here, if you were to literally do that, like slide across the floor, it's the exact same answer as a truck sliding on ice. You follow?
Yeah.
I did it last year in my course with the work kinetic energy camera. Remember Tom Cruise comes in with a guitar, I said? He slides in Risky Business. It's like a scene in Risky Business, an older movie, where Tom Cruise slides in with socks across a wooden floor. And he like glides across the floor. So I posed that question. Isn't that like such a fun thing to do, put on a new pair of socks and just like go sliding around in your house if you have wooden floors? Because you just glide everywhere. It's the same exact problem as this, right? No? So if you could model this problem where something is moving, like this pen right here, that's the same problem we just did. Exact same problem right there. Calculator, same one. Higher mu value, clearly. Right? I mean, really, right? Much higher mu value. Stopped almost instantaneously from when I let it go. Now, let's take a look at part C though. Max, can.
Where does mu come from?
Mu is given in the problem up here.
But like,
It's the
how
composition
do
of the two
you-
surfaces. It's
it
all
can
experimentally
be bigger than
determined.
one.
Say it?
Can it be bigger than one?
Yes, it can actually. Mu cannot be negative, but it could be greater than 1. That would be very, very, very high friction surfaces. There are values. And mu s is greater than mu k. Static friction between two surfaces is greater than kinetic friction. And it's really all the ridges that are microscopic that are overlapping with one another. All determined experimentally. So if you want to know like the mu value of ice on glass, you have to physically do it and see what it is. I'd like to do it. Maybe tomorrow, if you guys hang around after school when we do office hours, I could also just bring out the ramp and show you how you release the minimum and start calculating static on the ramp. We're definitely going to do it as a fall on that, because we might not have time for the test to do it, which I don't think we're going to have time. Part C, let's take a look at how part C would change. So I want to generally use the same thing though. I don't want to go into too much work or do too much work. So already what I want to recognize is some stuff that's happening here. So first, if I look back up here, this is still valid for part C. I'm considering down the ramp the x direction, remember. Down the ramp is the x direction. So if I want to know how far down an inclined plane a truck would slide before it eventually stopped, I would have to use this equation right here still. It's my A that's going to change now. It's my A that'll change. This will still be 10. This will still be the same general equation of a solution, but A is going to change. By the way, numbers-wise, your text has the answers because this is one of the samples out of your text. But this is around 8.5 meters. This is around 50 meters. That's the difference that comes out to be. So just adding ice to a surface, instead of taking 8 meters, which is like not that far, 8 meters is like the distance across the room it would take to stop, going 10 meters per second, which is actually not that fast to start. It's still going to take you the distance across the room. But the minute you throw ice down, we're talking 6 times as far, because the composition goes down by a factor of 6. You all see the numbers here, how the math works? 0.6 to 0.1. So now I'm dividing by a number 6 times smaller, so my answer should be 6 times larger. These might not be exact, by the way. I forget what they were. I'm just pulling them out of my head from the text. Now, if we have a car sliding down an icy hill, we now have to think about the fact that this is our diagram right here. There's our diagram. And there's the positive x, and there's the negative x. Okay, that's my diagram. So what else is a force affecting this car now? Friction still opposes its motion, right? Friction is going to push the car back up. It's sliding down the hill. Friction definitely pushes back up. What other force, though, now affects the x motion?
Sine of gravity.
Nice. Fg sine theta. Very good. The x component of the weight. Remember that the free body diagram on this truck now looks like the following. Fg cos theta. This is Fg sine theta. This is still Fn, but it's acting out of the ramp. And this is still Ffk. And I should draw my positive in the y direction and negative in the y. This is going to be the negative y, and up here is the positive y. Kind of squeezing it in there, sorry. There's the positive y symbol right there. And here's the negative y symbol at the bottom there. Max.
So does the speedometer calculate, like, does it keep that? Does it count Fg sine theta? It does, right?
Does the speedometer to keep it?
On a car. Like if you're going down.
Yes, because it uses what's called a tachometer. It's measuring revolutions, and it knows the circumference of your tire. So every time one click goes by, it knows how far you've traveled in that small amount of time.
So if you slide though, it doesn't calculate this?
Yeah, that's interesting actually, Max. So if you slammed on the brakes, right, and your car was sliding and the brakes were locked, it would probably measure you as 0 velocity or speed as you're going through that. It's a really good question. Interesting. Yeah.
Then if you're like spinning on ice, wouldn't that mean your speedometer would be registering like 100 miles an hour? You're not going anywhere. You're just like spinning.
Yeah, like if you hit the gas and your cars are spinning in mud, your tires are spinning in mud, I think you still see the speedometer go up actually. I'm not sure. I'm saying it like I know it, but I think that's right. Look up the phrase tachometer. Pretty sure a tachometer is what's used to eventually measure the amount of, whatever, we're getting into too much side notes, but I think it also used to measure distance traveled as well. You know, you see the mileage on your car?
Yeah. Because I know they have those machines that measure like torque, whatever, where the wheels just like go on like 2 like different barrel type things, and then just like press the gas and bring it down.
And it probably measures the amount of force applied, and therefore at a distance it knows the amount of torque it can provide.
Yeah, but it just stays in place and like fast.
Yeah, the car itself doesn't move. Yeah, and that would make sense for torque, yep. All right, back to this problem though. The key is this. Let's take a look at the x direction. Now we've got the following. Negative ffk again, but now we've got plus fg sine theta. And that equals ma. So I'm going to highlight earlier in green, please. Take a look where I'm highlighting. That was the equation earlier. It was negative ffk equals max. Now we've got negative ffk plus the weight pulling down the ramp equals max. I should call that ax. It doesn't matter right now. Okay, so again, that's the major difference there. How about the y direction? What's the difference? What's the equation in the y direction now? Chip?
Well, your normal force is going to be less to move forward.
So what is the equation?
Fn minus Fg cosine theta is ma.
Which is really?
0.
So as Chip mentioned, take a look. And I'm going to highlight in blue. The equation we got in the y direction earlier was this right here in blue. Fn minus Fg. Well, this is really close. It's darn close, isn't it? But what do we know about cosine of any angle? It's never going to be greater than what number? Cosine and sine can never be greater than? 1. Yes, you have the finger up. Say it, 1. So this will always be either a fraction or 1, right? So if my angle is 5 degrees, the cosine of 5 degrees is a fraction. So your weight times some fraction is what Fn is. So Chip is 100% right. Your Fn is going to go down. because this is only a fraction, cosine theta, fraction of your weight. I need you to think cosine, adjacent over hypotenuse. Adjacent on a triangle is always less than hypotenuse, isn't it? So this cosine theta will always be a fraction less than or equal to 1. So you're getting a fraction of your weight, which is what Fn is now. But we still have to complete the problem. So Fn becomes equal to Fg cosine theta, which is mg cosine theta, really. That's what Fn is. Well, Fn is going to go in over here in this equation. Take a look at the equation we've got now. We're going to take what we solved for just now as Fn right here. I'm going to plug it into the x direction like we did earlier. It's the same process. It doesn't change. I find Fn in the y like we did earlier. And we took Fn and plugged it into the x, right? Remember we did that earlier? We're doing the same darn thing. I'm plugging in a step early, I guess. Earlier, last time I solved for ax. What's the difference really, right? Negative mu k times mg cosine theta plus mg sine theta equals max. What's in every term? M. Cancel it, please, because it's in every single term.
So for a lot of these problems, it's just about subbing in. For a lot of incline problems.
Well, once you set up the equation, yes. But yeah, the equation in the x changed now because weight is pulling down the ramp, and the equation in the y changed because the normal force is now only a fraction of the weight. But then after that, it's about substitution method and solving the equation. Absolutely. Okay, and again, if you want to solve these when you get to the equation point and you want to plug in all numbers, that's fine. You can use your calculator to solve, but in this case, it's pretty easy to solve for A. Right? If I look at the solution for A now, here it is. That's the whole solution. Negative mu k g cosine theta plus g sine theta. I mean, look how much that differs. I'm going to highlight in yellow right now my last generic solution earlier. Where was it? Let's see. Here it was, right there. It's tough to see. I'll point to it. That was our solution for acceleration when it was on a flat ground. Just negative mu k times g. And that's here. Where is it, guys? It's right here. Look. There it is. And if we're a flat ground, what would theta be? And what's the cosine of 0 equal to? And what's the sine of 0 equal to? So this whole thing would drop off. This would become a 1, which leaves us with just this, doesn't it? And isn't that what we have right up here? So when it's on a flat ground, you could use the inclined plane solution for acceleration, really, and just set theta equal to 0. This drops off. This becomes a 1. You're left with negative mu kg, which is what we had up here, negative mu kg. So really, this is the more powerful solution, right? And we could just say, oh, if the a equals 0, it's flat. And this drops off, and this becomes a 1, and there's our answer. Now, we're going to take that same a, this entire expression, I'm going to now circle in green. And we're going to take that, and that's going to plug in all the way back up here for a. Okay, I'm going to take that a, that whole expression, and plug it all the way back up in there to get delta x. And you know what? The answer for this, for delta x, is going to turn out to be around 500 meters. Yeah, I agree. Why? What's the comparison we're trying to make here? Look at it. I mean, come on. You only go up 5-degree incline, and your stopping distance is 10 times as much. That's the big key here. A slight incline of only 5 degrees, and we're talking about over 5 football fields in length to stop. 5 football fields. That's how far. Over that value, actually. Okay? Actually, over. Yeah. A meter is more than a yard, right? A meter is 3.28 feet, so it's more than a yard. So more than 5 football fields if it's on a slight incline. You know what? I'm really interested. I'm really intrigued by this problem. And I want to know, what if I change theta and make it 2 degrees now? Look at that. Just change that to 2 degrees, and that changes A. Or just change the generic solution for delta x. Right, here's the generic delta x solution. Let's write it out so we can all see it. This is what delta x would become for an inclined plane. The numerator doesn't change, but that denominator is now this entire thing. Right? There's the solution. That is the generic solution for delta x right here. So if I want to just parameterize the angle and sit there all day and practice and say, oh, I want to know what 1 degree is going to be, what 2 degrees, what 3 degrees, what 4 degrees, I could sit here and just keep changing theta and see how long, or how far, I should say, it will take for it to stop. So at 5 degrees, it'll take 10 times as long of a distance to stop. Okay, we got one more problem. I think we're probably close to time, but I'm going to start it anyway. We got one more. Any questions on this one? This is a sample question out of 6-1. So you can see the worked out part in 6-1, but obviously I've worked it out for you here. So let's look at this last one here where we've got now a pulley with multiple masses and with friction. In figures, blah, 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 block A and B have given weights respectively. Determine the minimum weight of block C to keep A from sliding. To keep it from sliding. So what kind of friction already do we have? If it's not going to slide. Static friction. Okay, so let's take a look and think about free body diagram. So let's take a look at block A first. We've got tension pulling right. Where is that tension coming from?
B.
Good, but it's not B that's affecting block A, right?
Yeah.
So we're not going to write the weight of block B acting on block A, because it's not. The tension in the rope, which is coming from block B's weight, is what's acting on block A. Now, what's opposing motion we said is friction. It's keeping it here. What's acting up and down in this problem? We've got normal force acting up for sure. How about acting down?
It's weight and the weight of C.
Very good. I'm drawing them both on the bottom. I know that block C is on top. Trust me, I can see it, and I know you can see it. But I like to draw all my vectors usually away from the center of mass. So I'm drawing it that way. If you want to put FGC up top and have an arrow going down and have that like colliding with FN, you can do that. I just think it's more clear to write it this way. Tristan, focus, come on. You looking? Okay, good. I just want to make sure you're looking. I want to see up. So if I'm looking at this, I want to see that you guys understand that this can go on the bottom. It doesn't have to go on top. Vectors don't matter where they're placed vertically if they're in the same direction. Now for block B, or for mass B here, we can see that all we have is the tension acting up and the weight of block B acting down. So it's really important to recognize how simple this equation is for mass B, especially when it's stationary. Because when these are stationary, what happens to my acceleration for both blocks? They go to 0. No acceleration. So let's look at block A. Okay, let's look at block A's equations of motion here. Block A, I know the following. In the y direction, I've got Fn minus FGA minus FGC equals MA. That's going to go to 0. Again, this is sum of the forces in the y direction for block A. And I'm literally listing them, like I keep saying, positive, negative, because of my free body diagram. Now, this is where it's going to get a little interesting when we look at this problem. In the x direction, we have to talk about what's positive and what's negative on our free body diagram, because it may not agree with mass B in a little bit. So I'm going to call this positive simply because it's showing the positive x. Now, theoretically, I should really just make that negative x so it agrees with block B. Because look at block B. We're going to be calling this negative in a little bit, and that's going to be positive for block B, isn't it? So think about it for a moment. If the whole system were to move clockwise, this one would be moving with a negative acceleration. Wouldn't we want this one to also be a negative acceleration so they agree actually? So if my surface were inclined, down the incline would be positive, wouldn't it be said? So I'm going to make this negative, even though that's the traditional way I would draw. X would be normally positive. But for this problem, I'm going to make this the positive x, and I'm going to make the right side the negative x direction. And again, the only reason I'm doing that is so that my signs agree with the other one. Remember, I'm not looking at my y direction signs for this and trying to get them to agree, because in the y direction, block A is going to be stationary, whether it moves left to right or not. In the vertical direction, it's not going to move. Okay, so this is very unique what I'm doing here. It's very rare that I'm switching and making the positive x direction negative, actually, but I'm doing it for that reason. I know the system is not going to rotate this way. Like, everybody agree with me? It's definitely not going to rotate this way. But if it were to hypothetically rotate this way, then this one would be moving in the positive acceleration. This would be moving in the positive acceleration. So the signs agree. So it's nice to draw my signs so that if the system moved, they would agree with accelerations. Okay, and I mean agree as in agree in the direction. Matt.
Should you always do that?
I would highly recommend it, or else what you're going to have to do is you're going to have to put a negative a in for one of the equations of motion, which we're going to show in a moment, and for the other one we're going to have to put a positive a. And you have to kind of remember to do that instead. So what I would do is this. Again, sum of the forces in the x direction for block A. We've got in the x direction friction pulling back. We've got tension pulling to the right. And this is what it's going to equal right here. Go ahead.
Is that negative? Is it tension negative?
Thank you. Sorry. We've got friction pulling left, which is positive in this case, and tension pulling negative. Tristan, very good. Thank you. So this is going to be negative in this circumstance because we're calling, again, to the left. We're calling back positive. So this is acting positively, and this is acting that way, which we're calling negative. Very good. Now, I'm going to leave my MAX alone for now. We know that it's stationary for part A, so I can make this 0 for part A. In part B, it's not going to be. It's going to be moving in part B, so we're going to have to see how that plays a role in part B. So I agree. In part A, we're going to see that. Now, for the other block, Spence, go ahead.
I was gonna do for like solving for
Give me 1 second. For the other block, what we're going to notice here, we have the sum of the forces in the y direction. Again, this was all block A. This is now going to be block B that we're looking at. And that equals mb times the acceleration in the y direction. We know that we've got tension pulling up. We've got the weight of block B pulling down. And that's going to equal 0. Because again, it's stationary still. It's still stationary. So we've got 3 equations here right now. We've got 3 equations. We can get the tension right away. Right? Take a look here. Right? We can get the tension immediately. Because acceleration is 0. That's why it makes it easy. FGB can move over, and we know the weight of the second block is 22. It's given 22 newtons is the weight of the second mass, or mass B.
When you want to solve for FT, and then substitute FS in the right equation for FN.
Yep, so let's go ahead and see that. So what Spence is saying is let's go ahead and plug in what we know. We can write this as mu Fn. And then what we can do is we can take this and plug it in for tension. We can solve this for Fn up here. And we could take this expression here and plug that in for Fn right there. So Spencer was seeing that we're going to have one main governing equation. He's like, let's just plug into that at this point. So our goal in this problem is going to be to figure out the minimum weight of block C. So FGC, which is here, is going to be what we're going to solve for eventually, which is going to go in here. FGA is what's known. FGB is known. Mu S is known. So the only thing unknown is FGC once we plug those into this equation. This is going to change for the second part when the second block has acceleration, or when the system has acceleration of 0.15. Okay, because block C is going to be gone. This won't be here anymore, and the accelerations will have values. This will have a value, and so will this. Okay, I recommend that you practice going through the rest of this problem. Okay, I highly recommend that you practice going through the rest of it, just to test your skills, see how you're doing.
I think the kid never saw us. It was his